Countercurrent chromatography is a technique for the purification or extraction of components from a mixture. Unlike conventional chromatography, such as HPLC or flash chromatography, countercurrent chromatography has a liquid stationary phase held in place by the unique spinning motion of a coil. In countercurrent chromatography centrifuges, tubing is wound in a coil onto a drum, called a bobbin, which is rotated in planetary motion. That is to say, the bobbin is revolving around the central axis of the Sun gear, while simultaneously rotating about its own axis at the same angular velocity. A two-phase solvent system is placed inside the coil. A simple example of such a system would be heptane and water, but a more likely system for a purification might consist of heptane, ethyl acetate, methanol, and water. This gives a two-phase system, with an upper organic layer consisting mainly of heptane and ethyl acetate, and a lower aqueous layer consisting mainly of methanol and water. When the coil is rotated with the two-phase solvent system inside, the planetary motion creates a mixing effect, akin to the swish-swash motion that occurs when a tube of two liquids is tilted from side to side. The net result of this motion is the formation of waves and a wave mixing effect. As the coil travels through its planetary motion cycle, zones of mixing and settling move along the phases, coincident with the low and high accelerations caused by the epicyclic motion of the coil. The mixing zones are coincident with low accelerations and take the form of the waves mentioned earlier. The settling zones are coincident with high accelerations and take the form of a smooth interfacial area. When a sample is introduced into the centrifuge, it will experience an enormous number of mixing and settling steps. A typical countercurrent chromatography coil may have 30 loops and spin at 1,200 RPM. It will therefore undergo 2.16 million partitioning steps per hour. That is 30 loops times 1,200 revolutions per minute times 60 minutes in an hour. All this generates high-resolution separations based on each component's differential partitioning behavior in the phase system, which is characterized by the distribution ratio Kd. Determining the distribution ratios of the main components in a mixture allow the countercurrent chromatography purification to be predicted with amazing accuracy. Here we see a prediction of two components, eluting from the countercurrent chromatograph, one with a distribution ratio of 0.5, the other with a distribution ratio of 2. The synchronous planetary motion of the countercurrent chromatography bobbin has a special feature significant in the design of instruments. There is no twisting of the flow tubes linking the coil to the pump and detector. This is because the rotation of the bobbin about its own axis unwinds the twist produced by its motion around the Sun gear. This gives the instruments no rotating seals to cause trouble. Overall, the technique has a number of distinct advantages over traditional solid-phase chromatography, such as high loading capacity. Even the smallest countercurrent chromatography centrifuge of 5 milliliters capacity is capable of accepting an injection loading of 50 milligrams of crude material. No need to filter. Cell debris and particulates are tolerated. A one-step purification from a crude extract is possible. No columns to replace. The coils are robust and last the lifetime of the instrument. Far lower solvent consumption than HPLC of the same size. Furthermore, a simple analysis method allows complete recycling of the mobile phase, further reducing solvent consumption. No drifting peak retention over time. A fresh coil is made for each batch of runs. This makes it easier to satisfy the regulatory authorities when purifying under good manufacturing practice regulations. No loss of components from irreversible adsorption. The recovery of components is always 100%. predictable scale-up from milligram to kilogram quantities. In line with most preparative techniques, some preliminary studies have to be performed before the crude material is injected into the instrument. Predominantly, this consists of identifying a suitable two-phase solvent system. At the Advanced Bioprocessing Center, here at the Brunel Institute for Bioengineering, we've developed a systematic step-by-step protocol that takes an inexperienced user logically through the process. The solvent selection part has been fully automated, using a liquid handling robot and HPLC or GC, allowing the selection process to be operated automatically without anyone being present. Appropriate phase systems are selected by screening a graded range of solvent systems to identify one with a suitable distribution ratio for the compound of interest. This shows a selection table, which covers a range from moderately polar, butanol and water, to non-polar, heptane and methanol. Alternative tables exist for extremely polar and extremely non-polar compounds, and also for employing different solvents to improve solubility. When using the liquid handling robot, all systems are made up in 4 milliliter volume. After phase separation, samples are taken from the top and bottom phases, analyzed by an appropriate assay, which is frequently HPLC or gas chromatography, and distribution ratios calculated from the peaks detected in each solvent system. The whole process takes several hours, depending primarily on the length of each analysis assay. But its automated nature means it can operate unattended, even overnight, and the operator need only look through the data to determine the best solvent system to use. When the distribution ratios for all solvent systems in a particular table are studied, a value of less than 0.2 will make the compound elute very quickly, not giving it much chance to separate from the other components. On the other hand, a value of greater than 5 will mean long elution times and possible band broadening. The degree of separation between the target compound and any of its contaminants can readily be calculated from alpha, the separation factor. Furthermore, once the performance of a particular countercurrent chromatography instrument under various run conditions has been observed, it's relatively easy to predict the minimum alpha value necessary for a given purification, helping in the selection of the best solvent system to use. Having determined the best solvent system to use for a separation, the process can be immediately scaled up to pilot level. At this magnitude, countercurrent chromatography can be operated in normal batch mode, or in certain circumstances, using a non-stop injection of the mixture for a continuous purification process. Taking full advantage of the liquid nature of the stationary phase, the technique being employed here is known as intermittent true moving bed. By flowing the upper phase in one direction, then the lower phase in the other direction, then the upper phase in the first direction again, and so on, a binary mixture can be made to separate into its components. One component will elute with the upper phase at one end of the countercurrent chromatography coil. The other component will elute with the lower phase at the other end of the coil. The mixture can be continually injected into the instrument, and thus it is a continuous purification process. In this case, a mixture of two dyes, one yellow, one blue, is being injected into the maxi centrifuge, dissolved in the upper phase as a green solution. The operator for this process is working from the safety and comfort of a remote operator room, from which he can see all the equipment and control it by computer, without having to handle any unpleasant or dangerous chemicals. A single dedicated software screen shows all the equipment and what is occurring at the time. Whilst still injecting the green mixture of dyes onto the coil at a rate of 200 milliliters a minute, the upper phase is flowed one direction for a period of 2 minutes, then the pump valves switch over and the lower phase is flowed in the other direction for a period of 2 minutes. The two dyes separate, and pure blue dye elutes at one end of the coil, while pure yellow dye elutes at the other end. Of course, a more complex mixture of components requires a batch mode of operation. In one example, the highly polar glucosinolate glucoraphanin was purified from a crude gum, and from the almost identical component glucoiberin by the maxi centrifuge. The injection loading for this separation was in excess of 250 grams per run. A combination of the extremely polar nature of the target molecule and the viscous and insoluble character of the crude gum meant that no suitable preparative method was found with solid phase chromatography, despite much research being done. Fortunately, the maxi centrifuge coped with it all. In just over 8 weeks, including all the sample preparation, analysis, evaporation, and report writing, 2 people managed to produce over 2 kilograms of pure glucoraphanin, the target compound, using the 5-litre maxi at the Brunel Institute for Bioengineering. With an even larger 18-litre super maxi now functioning at the Institute for Bioengineering, even greater injection quantities are possible. And research has shown that the size limit for this technique has not been reached yet. Countercurrent chromatography is an emerging technique of the future, one that is generating considerable interest across both academic and industrial organizations. On the one hand, engineering developments on the old J-type centrifuges have produced robust machines capable of separations which are fast, efficient, and able to accept extremely high loadings. On the other hand, developments in the application of the technique have produced protocols and solvent selection tables that make the determination of the separation conditions and the running of the instruments systematic and simple. Combined, these have produced a technique that is ideally suited to large-scale preparative separations, with advantages over solid-phase techniques, such as the ability to accept particulates, and there being no columns to replace, and advantages over former liquid-liquid techniques, such as the high speed and high resolution. The Brunel Institute for Bioengineering is a financially self-supporting organization working at the interface of medicine, biotechnology, and engineering. Founded in 1983 by Professor Heinz Wolff, the institute is located on the campus of Brunel University in West London. The institute prides itself on its record for enabling technology and its ability to ensure its products are efficiently designed and prototyped, ready for immediate production into the marketplace to benefit the end user. Research into countercurrent chromatography and its applications is a major part of the work at the Brunel Institute for Bioengineering. Scientists and engineers at the institute have taken the previously unreliable and slow technique of countercurrent chromatography and turned it into a fast, modern, and effective approach suitable for direct scale-up to industrial levels. With 5 laboratories dedicated purely to research into countercurrent chromatography and centrifuges ranging in size from 5 milliliters to over 18 liters in capacity, the scale-up of the technique from milligram to kilogram and beyond has never been faster, easier, or more effective than it is today. Countercurrent chromatography is truly an emerging biotechnology technique of the future.